We now begin discussions of integration, and I will start this section by reviewing uh, definite integrals that you learned about in calculus before. So let's start by looking at the integral, let's say, I'm just going to do a specific example. Let's say I want to compute integral of x squared on the interval from 0, let's say, to some a. So actually, let's do it from a to b. And so the definition of a definite integral, as you might recall, basically is for functions that are positive, the definition is that the definite integral is going to be simply the area under the graph of a function. So in this case, it's going to be this area. Of course, if you try to compute this area directly, you will not succeed because this kind of a geometric figure is not of a simple kind where you have a ready-made formula that you learned in high school or somewhere. So we need to come up with some definition or some way of computing this area that will work for arbitrary functions like x squared in this case. Okay, so this is my f of x equal to x squared. And so let's recall what we did in order to compute this area. So you want to approximate the area, not compute it exactly, but to approximate it by shapes for which area computation is simple. The simple shape, simplest possible shape to use is a rectangle. And so what you do is you subdivide this interval AB into many pieces, right? So you can do it in a couple of different ways. You can decompose it into subintervals, interval from A to B, into subintervals that have the same length or a different length. So for our purposes here, I'm going to use intervals of possibly different length. So I'm going to call A x0. I'm going to call B xn. So it means that altogether I will have n plus 1 points, right? I'm starting from 0 and ending with n. And then you again subdivide this interval into a bunch of smaller intervals, and then label what is called the partition points by x1, x2, x3, x4, etc. And so those points then are going to provide us with areas, so with bases of rectangles that we're going to use to approximate the overall area. All right, so then in addition to this, I'm also going to select more points in the interval from x0 to x1. So in the first interval, I'm going to pick this blue point and I'm going to call it x1 star. In a second interval, again randomly, I'm going to pick another point, call it x2 star. In a third interval, I'm going to do the same thing. Pick some point here, call it x3 star, and I'll continue in the same manner. I'm going to select a point inside each interval, like this. And so then we're ready to design rectangles here. So on a first interval, I'm going to use the blue point as a point at which I'm going to figure out the height of my function, of my rectangle. On the second interval, I'm going to do exactly the same thing. So the value at a blue point is going to give me the height of the rectangle. So then rectangle is going to be like this. Same thing on the third interval. And I'm just going to keep going like this forever. So let's say on the fourth interval, I'm going to use the value of the function at the right endpoint. And so we continue like this. And so what we're going to get is partition of our area into rectangles, and for each rectangle I can compute the area. And so then if I add up areas of rectangles that I got here, then I should expect that the number that I'm going to get is going to be approximation of the actual area under the graph of x squared here. So area then is going to be approximately equal. So A is area under the graph of f of x over the interval AB. So what is this area? This area is going to be area of the first rectangle. So area of the first rectangle is its base. Base is going to be the length of the interval from x0 to x1. So it's x1 minus x0. And the height is, according to my selection, is value of the function at the blue function inside the blue point inside the first interval. So it's a value of the function at the point x1 star, right? And then base times the height is the area of the rectangle, so that does it for the first interval. What about the second interval? Again, a similar thing. I'm using f of x2 star as the height of the rectangle. Its base is x2 minus x1. And you continue like this. And then what is the last contribution here? There will be a last blue point that is f of xn star, and it will be multiplied by the length of the last interval. So that's the length from xn minus 1 to xn. Right, I did not draw the last rectangle, so let's do that. It's possibly something like this. Oops. Right, so that is the last rectangle, and so its height is going to be, let's say, again, I'm going to place xn star here somewhere. And so the height is xn, f of xn star, and the base is the distance from xn minus 1 to xn. And then, of course, I can use sigma notation to express this sum. So this is going to be equal to the sum, and from 1, let's not use n, k from 1 to n. of what? F of xn star times, on the first interval I get x1 minus x0, on the second interval x2 minus x1. So that means that for nth interval, I have to multiply this by the length of a segment from x and minus from x. Sorry, I'm confusing my indices here. So on the interval k, height of the rectangle is f of x k star, and the width is the distance between points xk minus 1 and xk that form the base of a rectangle. A sum like this, again, if you recall, is called a Riemann sum. All right, and so then you can try to make your approximation finer and finer, right? And as you make it finer and finer, then it seems that the accuracy of these computations should improve. And in the limit, you would expect that the approximation is going to converge to the actual area under the graph. And so then A should be equal to the limit of these sums here, right? Of these Riemann sums. In fact, let's give this some notation. I'm going to call this Sn. So that's a Riemann sum based on n intervals. So then A must be a limit of this Sn as what happens. So as the number of points goes to infinity. But in fact, you have to make sure that the distance between points, between all consecutive points, must go to 0, right? Because you want to make your approximation better somehow everywhere on the interval from A to B. So a typical way to express this fact is to say that I want something called norm of the partition to go to 0. So area then is going to, and I'm going to define norm of a partition in a moment. Let me use a capital S here. So if this limit exists, this only makes sense if this limit exists. And if it does, then we typically say that the function is going to be integrable. By the way, and again, norm of a partition. So here, is equal to the length of the longest interval in partition P, where P is basically these points A equal to x0 less than x1 less than x2 less than etc. less than xn minus 1 less than xn, which itself is equal to b. All right, so that's how we defined, how we computed area under the graph of an arbitrary function. Well, and then this basically is going to be a definition of the definite integral, right? So a definite integral is defined precisely in this way, as a difference between areas under the graph of the function where the function is positive and minus the area above the graph of the function and below the x-axis where the function is negative. Okay, so let's look at this definition and see if we now want to prove things rigorously, how should we do this? So at this point we know the definition of a limit, right? So in principle we should be able to take a limit of a function or the limit of a sequence. So in this case it's the limit of a sequence of Riemann sums. But this might not actually be very simple, right? Because essentially what you want to do is to take a limit of expressions like that. And really we have not discussed how you take a limit like this, right? Because as you go from partition with n points to a partition that has n plus 1 points, the next partition in principle has nothing to do, doesn't have anything to do with the previous partition. And if that is the case, then really, how exactly am I going to take a limit when the largest interval in my partition goes to 0 of that? I don't really have, this equation has no meaning. Okay? Taking a limit like this has no meaning. One argument is that, so I'm basically free, like I said, I'm free to choose partition points, but in principle also I'm free to choose points at which I evaluate the height of the function, the height of the rectangle, right? And in principle I can select any point inside a given interval as one possible choice for xk star. And if I change my mind and then I select some other point or some other points for xk star within different subintervals, right? If I choose height in a different way here, here, and so on, then why should it have to follow that when I construct this approximation and I let n go to infinity, or if I let norm of a partition, length of a largest interval to go to 0, how exactly am I going to compute the limit of the circled expression? We haven't done anything remotely similar to this. So we have to come up with, if possible, with maybe some other definition of the integral that would be easy to deal with. On one hand, that it will be intuitive, and for which the techniques of taking limits and so on would make sense, right? So for which the stuff that we have learned so far would make proofs meaningful, right? Because right now we have no clue how to operate with objects like this. Okay, so let me then try to do something different, and I'm going to do it in the next lecture. So this lecture is just should serve just as a motivation of what will follow. I'm going to try to work a little bit more with a function f of x equal to x squared and see if I can be somehow smart in selecting my partitions and selecting this star points. Maybe that will be helpful in designing a definition of the integral that will work for any function that will be manageable from the point of view of a theory.